On scales far beyond the realm of human perception, there exist mysterious entities, breathtaking structures, and landscapes that defy imagination. These strange beasts and exquisite palaces inhabit both the microscopic and the cosmic realms. Some of these astonishing phenomena are just a few thousandths of a millimeter in size, invisible to the naked eye, while others dominate the unimaginable expanses of the cosmos, spanning distances measured in millions or even billions of light years. Thanks to groundbreaking new technologies, humanity now possesses the tools to uncover and explore these hidden worlds that reveal themselves only when we extend our vision far beyond the ordinary. Each one of these luminous specks in the sky, mere points to the unaided eye, represents an entire galaxy, home to billions of stars, planets, and potentially life-bearing systems. We are essentially receiving a daily stream of information from the universe, as if the cosmos itself were sending us an email filled with secrets yet to be decoded. By exploring both the tiniest particles and the largest galactic structures, we begin to understand how the fundamental laws of physics play out in unusual and often bizarre ways. These cosmic laws, seemingly rigid on Earth, can lead to counterintuitive consequences when examined at extreme scales. This journey of discovery carries us to the very frontiers of modern science, revealing not only our latest findings, but also presenting us with new questions, enigmas, and unsolved mysteries that continue to challenge even the most brilliant minds. This is the story of how the universe functions on scales we can't normally see, from nanoparticles to galactic superclusters. When we push our investigations beyond what our eyes and tools were originally designed to perceive, we find that the universe behaves in extraordinary, almost magical, ways. But humanity's understanding of the cosmos wasn't always so sophisticated. Just 3 centuries ago, when mechanical models like the orrery were first created, our knowledge of the universe was profoundly limited. An orrery is a beautifully intricate mechanical model of the solar system, designed to show the motion of planets around the sun. However, while impressive in appearance, such models are not to scale. The relative sizes of planets and the distances between them are drastically misrepresented. To illustrate this disparity, imagine shrinking Earth down to the size of a football. Since the real Earth is approximately 12,700 kilometers in diameter, this scale would represent a reduction by a factor of 60 million. Now, if we were to apply the same reduction to the Sun, we could visualize the startling inaccuracy of the traditional orrery. The actual Sun, more than 100 times the diameter of Earth, would appear vastly larger. In fact, over 1 million Earths could fit inside the Sun. Its immense gravitational force governs the entire solar system, holding the planets in their orbits like a puppeteer controlling marionettes. On this football-sized Earth scale, the Sun would not be right next to the planet like in the orrery. It would actually need to be positioned about 2.5 kilometers away. The actual distance between Earth and the Sun, approximately 150 million kilometers, is so vast that conventional units like kilometers quickly become impractical in astronomy. As a result, scientists use a special unit of measure, the astronomical unit, AU, which is defined as the average distance from the Earth to the Sun. With this unit, we can better grasp the vastness of space. Mars, for example, orbits at about $1.50. The asteroid belt lies between 2 and 3 Australian dollars. Jupiter, the solar system's largest planet, orbits at around 5 Australian dollars. Saturn follows at 10 Australian dollars, Uranus at 20 Australian dollars, and Neptune, our most distant known planet, resides about 30 Australian dollars from the Sun. Many people believe this marks the edge of the solar system. However, the reality is far more intriguing. If one continues outward to approximately 120 Australian dollars, they encounter a colossal and mysterious boundary, the heliosphere. The heliosphere is a vast bubble of charged particles emanating from the Sun. It was only confirmed in the mid-20th century, but earlier astronomers had already observed clues hinting at its existence. These clues came from the behavior of comets, icy bodies of rock and dust that orbit the Sun in highly elliptical paths. Comets are known for developing 2 tails as they approach the Sun, one made of dust and another called the ion tail, composed of gases. Curiously, the ion tail always points directly away from the sun, no matter the comet's trajectory. This strange behavior puzzled early scientists. How could the sun be blowing a wind in the vacuum of space? Isn't space supposed to be empty? The answer lies in one of the most dramatic and powerful phenomena the sun produces, its outer atmosphere, known as the corona. During a total solar eclipse, the corona becomes visible to the naked eye as a ghostly halo of light. It consists of massive ejections, arcs, and flares of plasma, a superheated, electrically charged form of gas. This plasma, energized by the sun's magnetic field, escapes the gravitational pull of the sun and flows outward at immense speeds, forming what we now call the solar wind. At its root, the solar wind is driven by the sun's complex and ever-changing magnetic field. Much like Earth's magnetic field, but far more intense and dynamic. The sun's magnetic lines twist and loop across its surface. At the equator, these loops tend to close in on themselves, but at the poles, they often stretch far into space. As plasma particles accelerate along these lines, they eventually break free of the sun's grip and flood the solar system, contributing to the formation of the heliosphere. This vast magnetic bubble serves as a protective shield, deflecting harmful cosmic radiation and charged particles away from the planets, Earth included. To help visualize this concept, scientists often use fluid dynamics analogies. Imagine a hose spraying water in all directions into a pan of water. The new water forms a turbulent boundary as it collides with the water already in the pan. This is similar to how the solar wind interacts with the interstellar medium, the thin soup of gas, dust, and plasma that fills the space between stars. Though we think of space as empty, it's actually filled with these minute particles. As the solar wind encounters the interstellar medium, it forms a boundary layer, creating a natural shield that wraps around the solar system. This shield, the heliosphere, acts like a cosmic life raft, carrying the planets through a sea of interstellar material. Like the hull of a ship slicing through water, the heliosphere protects us from cosmic debris, high-energy particles, and interstellar radiation. Even more remarkable is that the heliosphere forms a bow wave, much like the wake formed by a ship's prow, as it plows through the galaxy. Observations have even revealed similar structures around other stars, suggesting that heliospheres might be a common feature of stellar systems. In 2020, the European Space Agency launched a mission specifically designed to study the Sun, the Solar Orbiter. This advanced spacecraft, developed with contributions from scientists at Imperial College London, carries a suite of instruments including cameras, sensors, and a highly sensitive magnetometer. The latter, which measures the sun's magnetic field, is crucial for understanding how solar wind is generated. Engineers had to develop innovative techniques to protect the orbiter's instruments from the intense heat near the sun, including a high-tech heat shield that maintains the spacecraft's core at a stable temperature. As the solar orbiter relays its findings back to Earth, scientists are beginning to gain new insights into how the sun's magnetic field operates and how it shapes the heliosphere that surrounds us. These daily data streams are, in essence, a constant message from the frontier of our solar system, revealing how the solar wind, solar flares, and the magnetic field interact to create the environment in which we live. Farther still, beyond the heliosphere, at distances of around 100,000 Australian dollars, we encounter what many astronomers believe is the final structure of the solar system, the Oort cloud. This is a theoretical sphere of icy bodies that may extend up to 3 light-years in diameter. The objects in the Oort cloud are thought to be remnants from the solar system's formation, lying dormant in the cold and darkness. At these scales, we switch from using astronomical units to light-years, the distance light travels in 1 Earth year, or about 9.46 trillion kilometers. Leaving the solar system entirely, we step into the galaxy that contains it, the Milky Way. A century ago, many astronomers believed the universe consisted solely of the Milky Way, and that what we now recognize as other galaxies were merely clouds of gas and dust. These mysterious smudges in the sky, called nebulae, sparked fierce debate. Were they close clusters of stars, or separate galaxies in their own right? The answer came from the brilliant work of Henrietta Swan Leavitt, who discovered that a specific type of star, known as a Cepheid variable, pulses in a predictable pattern, and that the rate of pulsation is directly related to its intrinsic brightness. This relationship meant that by observing a Cepheid's pulse, astronomers could determine how far away it was. This breakthrough enabled Edwin Hubble to prove that the Andromeda Nebula was actually a separate galaxy, millions of light years beyond the Milky Way. Suddenly, the universe exploded in size. Galaxies were no longer a curiosity. They were the fundamental building blocks of the cosmos. And there were billions of them.